complexity of beta plane zonal jets. So, Laura, you have the floor.
Thanks very much to the organisers for the invitation to speak today. So yes, I'm Laura Cope, and today I'm going to talk about some work that I mostly did during my PhD here at the University of Cambridge, where I was working with Peter Haynes, looking at the variability of zonal jets. As we saw earlier today, zonal jets are strong currents in fluid flowing in the east-west direction. And the video on my slide here shows the atmosphere of Jupiter. And the alternating currents that you can see are zonal jets or jet streams. Jets naturally arise in a variety of geophysical fluids, both on Earth and other planets in the solar system. For example, we've observed jet streams in the atmospheres of Jupiter and Saturn. And on Earth, we have, for example, the mid-latitude jet stream in the Earth's atmosphere, and there are multiple jets in the Antarctic circumpolar current. Now, the mid-latitude jet stream in the Earth's atmosphere plays a key role in our climate system, and so understanding its behaviour or its time variability is one of the major factors towards understanding our climate. And this leads me on to the main question that I was trying to answer in this research, which is, what insights can we learn about the time variability of jet streams using idealized models? Observations of jet streams throughout the solar system reveal different types of variability and also different timescales of variability. So, for example, on Jupiter, the jet streams are observed to be very steady in both space and time. Now, over 20 years ago, the Voyager mission to Jupiter collected data looking at the strength of the zonally averaged winds, which I plotted here. And then about 20 years later, the Cassini mission also collected data looking at these winds, and the two data sets are very similar, suggesting that the positions, the numbers, and the strengths of these jets have remained virtually constant over 2 decades. In the Earth's oceans, the jet streams are observed to vary over timescales of the order of months. And this can be seen in this figure here from this paper. Now, to explain the figure in more detail, what the authors have done is they've considered a single line of longitude between South Australia and Antarctica. And they've looked at the time evolution from left to right of the sea surface height anomalies through this longitudinal slice. And you can see that there is a certain amount of variability. So, for example, at this point in time, given by the white line, you can see 2 jets are merging to form a single jet here. And then just further south, you can see a new jet forming or nucleating. In the Earth's atmosphere, the jet streams are observed to vary over timescales of the order of days. And I've compiled this movie here using data from this website. And a single second corresponds to a single Earth day. And you can see a certain amount of variability on a daily basis. Okay, so the plan for my talk today is as follows. I'm going to begin by introducing a very simple, idealized, and fully non-linear model that allows for the spontaneous formation and equilibration of jets. And I'm going to show you the types of variability that exist within this system. I'm then going to consider a couple of reduced versions of this model by employing the quasi-linear and the generalized quasi-linear approximation, where I'm going to systematically neglect eddy-eddy interactions in order to try to understand aspects of variability. I'm then going to take a closer look at a spontaneous symmetry breaking phenomenon that emerges in my simulations. And then I'll give some additional insights into jet variability before concluding the talk. So let's begin by considering a very simple idealized model, and this will form the basis of all of the work in my talk today. But before I do so, I'd first of all like to introduce to you the concept of the beta plane approximation. So let's imagine a rotating planet with a planetary rotation vector aligned with the axis of rotation. Now, at any latitude on this planet, this rotation vector can be decomposed into a local vertical component and a local horizontal component. And it's the local vertical component that's important for the large-scale dynamics. And if we consider how this local vertical component varies with latitude, it decreases as you move from the pole down towards the equator. So there's a gradient. Now, it's common in idealized studies to treat this latitudinal gradient as being equal to a constant, which I'm going to call beta. And this is known as the beta plane tangent plane approximation. Okay, so this is a very broad summary of the model that I'm going to be talking about today. So I'm going to be considering a two-dimensional square domain of fluid, and I'm going to use doubly periodic boundary conditions. I'm going to incorporate planetary rotation by using a beta plane approximation, and I'm going to use a small-scale stochastic force as an idealization of small-scale turbulence. And then, because I'm going to continuously inject energy into the simulation through this stochastic force, I'm going to use friction as a dissipation mechanism. So these three components are the essential ingredients required for the spontaneous formation and equilibration of jets. So let's take a look now at a video which shows the spontaneous formation of jets in one of my simulations. So I'm continuously forcing at small scales, and you can start to see the emergence of some larger scale structures appearing. The yellow fluid is flowing to the east and the blue to the west. And these structures are becoming elongated in the zonal or the east-west direction. Now, at this point in time, you can see the emergence of two eastward jets here, an eastward jet here, and two blue westward flows. And shortly, these two jets are going to merge to form a single jet. And so in this particular simulation, we're going to equilibrate with two eastward jets and two blue westward flows. Now, to clarify, in my talk, I'm going to be focusing on the eastward jets, and I'm going to be studying their long-time behaviour. Okay, so mathematically speaking, the model can be written using a single equation of motion, the beta plane vorticity equation. And we have a term for the planetary rotation, a stochastic forcing function, linear friction, and then I'm incorporating hyperviscosity to remove the buildup of entropy at the smallest scales. And this system comprises three different parameters. So we have beta, which is the background gradient of potential vorticity. We've got the energy injection rate, epsilon, due to the forcing, and the damping rate, mu. And just a brief note about the stochastic forcing that I'm using in this system. It's white noise in time, and it's both isotropic and homogeneous. And I'm forcing a narrow annulus of wave vectors in Fourier space with a well-defined forcing wave number. Okay, I'd like to take just a brief moment to explain to you how you can interpret the results of the simulations that I've been running. So, on the left-hand side of the slide here, you can see snapshots in time of the zonal velocity field, where the yellow fluid is flowing to the east and the blue to the west. And if we compute the zonal average of these plots, we obtain the plots for the zonal mean zonal flow, or the jet velocity profile. And you can see that the jet that has appeared is located around here. Now, if we compute this profile at each instance in time, then we can plot these latitudes time plots, such as the one on the right-hand side here. And these show the spontaneous emergence of the jets and also different types of variability. Now, in this particular case, a single jet has formed, but we could vary the parameters, and so we could also see different numbers of jets appearing. Okay, so let's take a look at some results. So I've run this model over a broad range of different parameters, and I've tried to categorize the simulations according to the main types of behavior. So for example, we see randomly wandering jets. We also see jets merging and new jets forming or nucleating. However, we also see this new type of behavior. We see jet migration behavior. And in this particular example, a single jet has formed and it's systematically migrating either north or south with a fairly constant speed. And it also has the capacity to spontaneously change direction. So this is the first main result today, which is that we see this new type of variability. We see jet migration behavior. And I'm going to be focusing on this later on in the talk today. Okay, so you might like to see the parameter space that I've been exploring. But to do so, we first of all need to see what are the important parameters in the system. So to do this, let's imagine the flow of energy across different wave numbers or spatial scales in the system. So in each case, we're forcing the system with a characteristic forcing scale, which I'll call KF. And because this is a two-dimensional simulation, energy is going to isotropically flow to larger scales or smaller wave numbers via an energy cascade, the inverse energy cascade, with a k to the minus 5/3 spectrum. However, there becomes a length scale at which the effects of rotation start to become felt by the system. And this is given by this wave number here. Now, for smaller wave numbers, the energy is going to preferentially flow into the zonal rather than the latitudinal scales. And we're going to see a zonostrophic k to the minus 5 energy spectrum. And the energy cascade, the inverse energy cascade, stops at what we call the Rhine scale, given by this parameter here. And the Rhine scale differentiates the largest scales of motion, which are dominated by linear wave motions, from the inverse turbulent cascade. And there is evidence in my simulations for these different spectra. So for example, this is data from a single simulation, and you can see evidence for both the k to the minus 5/3 and the k to the minus 5 spectrum, with a large buildup of energy at around about the Rhine scale. Okay, so the Rhine scale is very widely believed to be associated with the spacing between the jets. And this can be seen from the data from my simulations. So for example, along the horizontal axis, I'm plotting the theoretical Rhine's wave number. And along the vertical axis, I'm plotting the observed number of jets in the simulations. And you can see that there's a clear linear relationship with a certain amount of variability. Okay, so the second key parameter, which I'd like to introduce to you, and Peter mentioned about this earlier, is the zonostrophy parameter. And this is defined to be the ratio of the length scale, or the wave number, at which the effects of rotation first become felt by the system, divided by the Rhine's wave number. And the zonostrophy parameter can be considered to be a measure of this zonostrophic cascade range. Now, for larger zonostrophy or larger zonostrophic cascade ranges, we see stronger jets. But for weaker zonostrophy or smaller zonostrophic cascade ranges, we see weaker jets. And this can also be seen using a very simple analytical model, which I'll explain to you. So let's consider decomposing the energy spectra into the contributions from the zonal mean flow and the contributions from the remaining zonal eddies. Then we're going to consider all wave numbers, and we're going to separate them according to whether they are smaller than or larger than the Rhine scale. Okay? For wave numbers smaller than the Rhine's wave number, we're going to let both spectra be equal to 0. For wave numbers larger than the Rhine scale, we're going to allow the energy spectrum for the zonal mean flow to follow the zonostrophic k to the minus 5 spectrum. And for the remaining zonal wave numbers, we're going to allow that spectrum follow the isotropic k to the minus 5/3 spectrum. Okay? So now we can compute the total kinetic energy in the zonal mean flow to be the integral over all wave numbers of the energy spectrum for the zonal mean flow. And likewise, the eddy kinetic energy is the integral over all wave numbers of the energy spectrum for the remaining zonal wave numbers. And then using these two quantities, we can calculate the fraction of energy in the mean flow or the zonal mean flow using this expression, which turns out to be this function of the zonostrophy parameter here. Now, this is an increasing function of zonostrophy, and it's shown on this plot here. So this is the analytical relationship we've just derived, plotted as a function of zonostrophy and the fraction of energy in the zonal mean flow. Now, each one of these circles represents a single simulation from my model. And you can see that they roughly follow the same type of relationship. However, they're color-coded according to the main types of behavior. And you can see that they all systematically lie below the curve, and there seems to be some sort of dependency on the type of variability exhibited. I'm going to return to this plot towards the end of my talk today. Okay, so finally, let's have a look now at the parameter space. So along the horizontal axis, I'm plotting the Rhine's wave number, which is our theoretical estimate of the number of jets, against the zonostrophy parameter. And each one of these circles corresponds to a single simulation that's color-coded according to the number of jets that we observed. Now, we might like to ask, how does this parameter space correspond to naturally occurring jet streams? So, for example, in the Earth's ocean, the zonostrophy is somewhere between 1 and 2. It's of a similar value for the Earth's oceans. However, values for Jupiter and the gas giant planets are much higher, with values of 5 or more recorded. Okay, so one question we might like to ask is, which out of these simulations show jet migration behavior? And it turns out to be these ones here. So you can see that migration is occurring over these sub-intervals of the Rhine's wave number scale. So we can summarize migration behavior in terms of our parameter space as follows. As the Rhine's wave number increases, so does the number of jets migrating. And as the zonostrophy parameter varies, well, for larger zonostrophy, the jets are found to behave more deterministically. But as the zonostrophy decreases, the jets behave more stochastically, so they're more inclined to change direction and more frequently. Okay, so let's now consider a couple of reduced versions of this fully nonlinear system and see what happens when we systematically neglect eddy-eddy interactions in order to try to understand aspects of variability that we've observed. So I'm going to begin with a discussion of the quasi-linear approximation. This has been widely used in physics for well over 50 years. And the idea is as follows. We're going to allow, in terms of zonal eddies or zonal wave numbers, nonlinear interactions between the zonal eddies and the zonal mean flow. But we're going to neglect all nonlinear interactions between the zonal eddies themselves. So mathematically speaking, we're going to decompose, for example, the stream function into the mean flow and the eddies. And then if we consider our original vorticity equation, written here in terms of linear and nonlinear operators, we can derive evolution equations for the mean flow and the eddies. And then the quasi-linear approximation neglects the eddy-eddy interaction terms from the evolution equation for the eddies. This is equivalent to neglecting these same interaction terms from the original vorticity equation. And so we can derive a quasi-linear vorticity equation that we can numerically solve using the previously described procedure. So let's take a look at some results. And just to recap, in the fully nonlinear system, we saw 3 types of behavior, okay? When we go to the quasi-linear model, we still observe the randomly wandering behavior and also the merging and nucleating behavior. However, we no longer observe jet migration behavior. So this is a clear distinction between the nonlinear and the quasi-linear system. And this can also be visualized with a couple of numerical simulations. So in each of these 2 cases, between the models, I'm keeping all of the parameters the same between them. And in each case, as I increase time from left to right, I'm also systematically increasing the value of beta. And so this in turn systematically increases the Rhines wave number. And so we would expect to see the number of jets increasing, and indeed it does in both cases. However, in the nonlinear system, as we transition from 1 jet to a 2-jet state, we see this migration regime. But we don't see the same behavior in the quasi-linear system, okay? Okay, so this is a clear distinction between the nonlinear and the quasi-linear model. But what happens if we consider an intermediate type model where, rather than neglecting all eddy-eddy interactions, we systematically neglect interactions? So to do this, we're going to use the generalized quasi-linear approximation. And the idea is as follows. We're going to consider all zonal scales in the system, from the zonal mean down to the smallest resolved zonal scales. And then we're going to separate these into 2 different sets. So in the first set, which I'm going to call the low modes, we're going to put the largest zonal scales. And then in the second set, which I'm going to call the high modes, we're going to put the remaining zonal scales. And we're going to define a separation wave number, lambda, where lambda is the largest wave number in the low modes. Now the trick is that we're going to allow fully nonlinear interactions between the low modes. But we're going to neglect certain interactions between the low and the high modes in such a way that we retain the original conservation properties of the system. So mathematically, the analysis is similar to the quasi-linear system. We're going to decompose the stream function into contributions from the low and the high modes, denoted with letters L and H. And then once again, we can decompose the vorticity equation into contributions from the low modes and the high modes. And then we're going to neglect interactions between the high modes in the evolution equation for the high modes. And as before, this amounts to neglecting these same interaction terms from the original vorticity equation. So this time we derive a generalized quasi-linear vorticity equation, which we can numerically integrate. So just to summarize the three different models, we have the fully nonlinear model, where we're allowing all possible nonlinear interactions. We've now got the generalized quasi-linear system, where we're allowing fully nonlinear interactions between the low modes. And we've also considered the quasi-linear system, where we only allow interactions directly back and forth between the zonal modes that are directly forced and the jets themselves. So let's take a look at this generalized quasi-linear framework. So here are 5 simulations. In each case, I'm keeping the parameters the same in all cases. The only difference is the value of the separation wave number lambda that I'm using. So in the bottom row here, this is a simulation from the fully nonlinear system. And you can see 2 jets are migrating north. In the top row, this is a simulation from the quasi-linear model, and as we would expect, the jets do not migrate. However, in these intermediate models, we see that the jets do migrate, and in fact, the properties of migration, such as the migration speed, are also retained. So this is the second main result in my talk, which is that migration requires lambda to be greater than or equal to 1 in the generalized quasi-linear framework. Okay, so let's now take a closer look at jet migration, which is a spontaneous symmetry breaking phenomenon. But before I do so, I'd like to introduce to you the concept of zonons. So, zonons are the generalization of Rossby waves to flows with latitudinal shear. And they can be thought of as follows. So let's decompose the stream function into the mean flow and perturbations away from the mean. Then, for small amplitude perturbations, we can derive the linearized perturbation equation here. Now, let's initially consider a system that contains no jets or no latitudinal shear. In that case, the mean flow will not depend on latitude y. And so this coefficient here will be equal to a constant. And so the solutions to this equation are plane wave solutions, i.e. linear Rossby waves. However, if the system does contain jets and hence latitudinal shear, then the mean flow will depend on y, and so this coefficient will also depend on y. And so in this case, these solutions, whilst they're still wave-like solutions in x, they now have a more general dependency on the latitude y. And these are what we call zonons. Now, in my simulations, alongside or coinciding with the jets, we see this meandering structure with zonal wave number equal to 1, which I'm associating with the zonons. In the nonlinear model, we're allowing all possible nonlinear interactions. Oops, my thing's gone. There we go. We're allowing all possible nonlinear interactions. And so in this system, we would expect to see the formation of zonons. In the generalized quasi-linear model, we're allowing all nonlinear interactions between the low modes. And so in this system, we would also expect to see the formation of zonons. However, in the quasi-linear model, we only allow interactions back and forth between the mean flow and the jets and the eddies that are directly forced. And so in this model, it's not actually clear whether or not we would expect to see the formation of zonons. And that is because of the forcing distribution that I'm using. And to explain that in more detail, this is what is happening in spectral space, okay? So we are forcing these wave vectors here, this annulus. Jets that emerge have zonal wave number equal to 0, so they would lie here. Zonons have zonal wave number equal to 1, so they would lie here. Now, in the quasi-linear model, let's consider an arbitrary wave vector, okay? So this is our wave vector. In terms of zonal wave numbers, this wave number can only interact back and forth with the mean flow. However, in terms of the latitudinal wave numbers, it can fully non-linearly interact. And so we would expect to see energy going into all of these modes. We can play the same game with other wave vectors and other wave vectors. And so you can see that in theory, energy does have the capacity to flow into all wave vectors inside our forcing distribution, okay? But in practice, what we observe is the following. In the fully nonlinear and the generalized quasi-linear models, we do see energy flowing into the mean flow and the largest zonal scales associated with the zonons. However, in the quasi-linear system, we only see energy predominantly flowing into the zonal mean flow itself. And so we're left to conclude that in the quasi-linear system, zonons are not forming. So this is another clear distinction between the nonlinear and the quasi-linear system. Okay, so let's take a closer look now at jet migration behavior. And there are a number of questions that we might like to ask. So for example, why do jets only migrate when lambda is greater than or equal to 1? Secondly, can we predict the speed at which the jets migrate? And then finally, do jets also migrate in more complex systems? Let's focus to begin with on question 1. So we're going to imagine 3 different situations involving a pair of jets. We're going to imagine 2 jets migrating north, 2 jets migrating south, and 2 non-migrating jets. And let's take a look at the center here at snapshots in time of the zonal velocity field. But actually what I've done is I've taken the square domain, I've squashed it in the zonal direction, and then I've tessellated it 4 times in order to visually enhance the physical features. And you can see that when the jets migrate north, there are these zonal flow anomalies on the northern side of the jets. When they migrate south, you see these anomalies on the southern side of the jets. And in this non-migrating case, well, one of the jets has anomalies on either side of it. And these features can also be visualized in the vorticity field, where when the jets are migrating north, we see these coherent patches of positive red vorticity on the northern side of the jets. When they migrate south, we instead see coherent patches of negative blue vorticity on the southern side of the jets. And in this non-migrating case, one of the jets is sandwiched between anomalies on either side of it. But are these vorticity anomalies coherent vortices, or are they waves? Well, to answer this, we need to consider the stream function. Or in fact, we need to consider the stream function in the frame of reference that moves with the jets. And that's illustrated on this right-hand side here. So moving with the jets, you see that the streamlines are actually open and they're not closed. And so we're left to deduce that these are actually large-scale waves in the system associated with a zonal wave number equal to 1. But why do the jets migrate? Well, to answer this, we need to consider the evolution equation for the jet velocity profile given here, where we see that the jets are forced by the Reynolds stress force. Now, I found an example of a simulation where in the first half, a pair of jets are migrating north, and then they spontaneously stopped migrating. So for each half of this simulation, I've computed time averages in frames of reference that move with the jets, the Reynolds stress force, which I'm showing in pink, and the jet velocity profile. And you can see that when the jets migrate north, both the Reynolds stress force and the jets are asymmetric about the axis of the jet, with this bulge on the northern side, which is the direction in which they're migrating. However, when the jets stop migrating, both the Reynolds stress force and the jets become symmetric about the axis of the jets. And so migration requires an asymmetric eddy forcing and a corresponding asymmetric mean flow. But to what extent are these asymmetries a direct result of the zonons themselves? Well, let's consider decomposing the eddy field into the contributions from the zonons with wave number equal to 1 and the contributions from the remaining zonal wave numbers. And then we can decompose the Reynolds stress force into the relative contributions from the zonons and the remaining zonal wave numbers. And then once again, we can consider a simulation where the jets are migrating north, and we can decompose the full Reynolds stress force into the contributions from the zonons and the remaining zonal wave numbers. And actually, what we see is that the zonons have a negligible contribution. The majority of the Reynolds stress force is coming from the remaining zonal wave numbers. And so we're left to deduce, and this is the third main result, which is that the zonons are actually playing an organizational role of the smaller scale eddies in the migration mechanism. Okay, so the second question. Can we predict the speed at which the jets migrate? So just to clarify, the migration speed is defined as the change in latitude of the position of the jet, delta y, divided by the time taken. We might hypothesize that the migration speed is some sort of function of the parameters in the system. And so I've collected data from a large number of numerical simulations across a broad range of parameters exhibiting different numbers of jets migrating. And empirically, it turns out that the migration speed is given by this expression here, which, when you rearrange this, is equal to the product of the damping rate times the Rhine scale. And this is verified on the right-hand side of the slide, where I'm plotting on log-log axes the migration speed against this expression here. Each one of these corresponds to a single simulation, color-coded according to the number of jets that were seen migrating, and you can see that there's a good relationship between the two. So this is the fourth main result in my talk, which is that the migration speed is given by an explicit expression, and it's proportional to the product of the damping rate and the Rhine scale. Okay, and then the third and final question is, do jets also migrate in more complex systems? And the answer is yes, they do. So for example, in general circulation models, studies have observed both the poleward migration of jets, so from the equator towards the poles, and also the equatorward migration of jets. And in terms of observations, well, I'm not aware of any observations of migration in, for example, the Earth's oceans, but there have been hints of migration in the Earth's atmosphere. So, for example, this study by Feldstein in 1998 looked at the time evolution of the zonally averaged angular momentum anomalies in the Earth's atmosphere. And you can see hints of migration from the equator down towards the South Pole. In this final part of the talk, I'd like to discuss some additional insights into jet variability. Or specifically, I'd like to return to this plot here from earlier in the talk, where, if you recall, I was looking at the relationship between the fraction of energy in the mean flow, or the strength of the jets, and the zoonostrophy parameter. And we noticed a couple of discrepancies. So firstly, all of the points lay below this theoretical relationship here. And there was also some sort of dependency on the type of variability. Okay? So to try and understand what's going on here, let's consider a couple of simulations. So in each case, I'm showing simulations where we observe a spontaneous regime transition taking place midway through the simulation. In these middle panels here, I'm plotting the time evolution of the kinetic energy in the zonal mean flow in this orange-yellow color here, the kinetic energy in the zonons in green, and the kinetic energy in the remaining zonal wave numbers in blue. And then I'm also plotting in red the combined energy in the mean flow and the zonons. And what we see is that the combined energy in the mean flow and the zonons is actually approximately constant in both cases. However, the relative fractions of energy in the mean flow and the zonons seem to depend on the type of regime that we are in. And so we might hypothesize that in fact, it's actually the combined fraction of energy in both the mean flow and the zonons that's important, rather than just the mean flow itself. So let's go back to our plot here. And let's now instead calculate the fraction of energy in both the mean flow plus the zonons. And that's what happens. As you can see, there is no longer any dependency on the type of variability, and all of the points are falling on our simple analytical relationship. So this is the fifth and final result in my talk today, that the zonons and the mean flow together define the zoonostrophy, and the variability in this model is linked to the relative strengths of these quantities. Okay, so just to conclude, the objective of this work was the study of jet stream variability. I used a very simple model which incorporates only the essential ingredients required for the spontaneous formation of jets. And I used a couple of different methods in order to try to understand aspects of variability. So I began by looking at the quasi-linear approximation, where I neglected all eddy-eddy interactions. And then I focused on the generalized quasi-linear approximation, where I systematically neglected eddy-eddy interactions. In terms of results, we see this new type of behavior, so migration behavior. Migration behavior and also the formation of zonons requires lambda to be greater than or equal to 1 in the generalized quasi-linear framework. The zonons were found to play an organizational role of the smaller scale eddies in the migration mechanism. The migration speed was found to be proportional to the damping rate times the Rhine scale. And then finally, in terms of variability more generally, well, there was a direct relationship between the zonostrophy and the fractions of energy in the mean flow and the zonons. And in terms of future work, there are a number of possible avenues here. So, for example, in terms of jet migration and zonons, can we use reduced models to gain additional insights into, for example, the source of the zonons? What are the nonlinear interactions that are important for the formation of zonons? In terms of merging and nucleating behavior, why do some models, such as this one, allow nucleation events to occur? But as we've seen throughout this program, other models do not allow nucleation. And does stochasticity have something to do with this? And then finally, what can we learn from more complex systems with additional physics? So, for example, including baroclinicity or spherical geometry. Thank you very much for your attention, and I'll be delighted to answer any questions that you may have.
Thank you. Very nice talk. In those observation examples that you saw, did you see any evidence for anomalies on one side of the jet?
I believe, I've had a look at some of the papers, and I do see the asymmetries present, yes.
How big is your domain in your simulations?
It's all non-dimensional.
Okay, but non-dimensionally, how big is it?
It's one.
No, this is
Okay, it's 2 pi by 2 pi.
2 pi by 2 pi. Okay, so you said when you were doing, you had a plot where you were comparing a nonlinear and your quasi-linear, and you were turning up beta. And you said in your nonlinear one, you got the migration when you switched from 1 to 2 jets. And I guess I'm wondering how much your finite domain size is coming into this, because you can only fit whole numbers of jets in there. And I'm wondering how much this migration thing is like a property of the fact that you have a fixed domain size versus something that, like you have some observational evidence, but like, is that really what we're seeing?
It's very difficult to disentangle because you've got doubly periodic geometry. What I will say is that we see it consistently with 1, 2, and 3 jets. And so anything that's happening, domain size effects typically come into play when you only have a single jet in the domain. Once you start to get multiple jets, there are other things going on as well, and there's less of an, I would say there's less of an influence of the boundary conditions coming into effect in that particular situation.
Have you ever tried like a bigger domain to see if this is a robust kind of scaling?
I personally have not changed the domain size, no. There are things you could try, for example. You could try an elongated domain. You could also try a longer domain in the latitudinal direction. These are things that are worth considering.
Could you elaborate on how the zonon organizes the turbulence of the non-zonon modes? And in particular, this seems critical to the story, and seemed to me an obvious first step, which I bet you've done, would be to look at the correlation of the zonon with the Reynolds stress, as it stands, produced by the non-zonon modes, right? In some sense, what's the spatial projection of that, and how does it correlate? Any comments?
So I haven't looked at the second part of what you've done, but that is certainly something that would be interesting to do. In terms of how the zonons are organizing the small-scale eddies, that's something I'm not too sure about at the moment. So if you have any ideas,
Well, the reason I propose this is that you say that the small-scale eddies ultimately are producing the stress.
Yeah.
So it seems that the zonon is breaking symmetry in the stress somehow. I mean, we in fusion have no shortage of things that do that. Okay, in the complicated mess that we live in, and this would seem to be the counterpart in this problem. Right, it's more a spontaneous symmetry breaking than a consequence of geometry or whatever.
Indeed, absolutely. But this is not something that I've looked at yet. I mean, certainly there's a lot more to investigate here, and the mechanism is not quite complete. And indeed, you're saying, understanding exactly what's going on, what's happening to the small scale eddies, these are all really, really important questions. But at the moment, unfortunately, I don't have any more answers for you.
So if you will, at some point you were showing the velocity profile of the jet in the case where they first migrate and then stop migrating. And it looked to me that the velocity profile of the two jets is almost identical when they are migrating, and it's different when they stop migrating. Do you understand it?
Can I just clarify exactly? If I go back. Is this what you're referring to?
Right. So in the migrating case,
Sorry, can you speak up a little bit louder so the rest of the hall can?
in the migrating case,
Yes.
the velocity profile of the two jets
Yes.
is very similar, while it seems different in the case where they stop migrating.
Yes.
And do you understand this? I mean, there is any comments that...
Yes, so the velocity profile itself, this quantity here is being forced by the Reynolds stress, okay? So if you see an asymmetry here, you're going to expect to see some sort of asymmetry here.
Right, but the two peak on the right are the same, while they are not when they stop migrating. I mean, if you wish, one of the two jets in the non-migrating case is much broader than the other.
Yes, these jets in the non-migrating case, I agree, they're not the same as each other, no.
So
But the point is that irrespective of the fact that this one has broader flanks than this one, they're both symmetric about this axis here. There's no north-south asymmetry.
Okay, so for you it's not surprising that the two jets in the non-migrating case are different.
Yeah, so in terms of in non-migrating cases, jets can take all different types of forms. Sometimes you get narrow ones, sometimes you get broader ones. That's completely expected and has been documented before. What's the point here is that they're symmetrical in terms of the north-south symmetry, but they're not symmetrical here.
Thanks, Laura, for the nice talk. I was just thinking about the migration speed and its relationship to the friction. And sort of something Peter showed earlier where he put in inhomogeneous friction spatially. Do you think the jets would adjust sort of instantaneously if you had half your domain at one friction and half at the other? Whether if you did then these kind of plots, you'd see like zigzags as the migration speed sort of instantaneously changed as it went over somewhere with different friction. Like you could imagine if this was an atmospheric jet, you have land and you have ocean, and they'd have different effective frictions in a simplified model. What might you expect? I guess you haven't thought about this.
Indeed, I haven't thought about it. It's a really, really interesting point, to be honest. I mean, I suppose the obvious answer is you would expect a change in translation speed. What I'm seeing at the moment, though, is that when the jets translate or migrate, they seem to be all doing it systematically. And whether they having different parameters in different regimes of the domain would allow that is another question. I'm not too sure, but it's something that would be interesting to have a look at. Yeah.
So I thought it was very appealing when you showed those observations with jet migration. I wonder if you can just go to that slide with the various observations.
Oh, sorry. Wrong one.
Yeah, it was later on in the talk.
Yeah, I know which one you mean.
I guess really what I would want to do is just hope you could elaborate on what we're looking at, especially in the leftmost and center plots.
Okay, these are Hofmöller plots. Okay, so just for the simulations in my talk, time evolves from left to right. Okay, in terms of latitude, we have the North Pole here, the equator here, and the South Pole here. Okay, so you can see that as time moves from left to right, these jet-like structures are migrating from the equator towards the North or the South Pole.
I guess it was more detail. So what are the colors? And is this the stratosphere or where are we looking?
This one here, I mean, this was an idealized study. I think it was just a very generic atmosphere, planetary atmosphere, to be honest. I think the authors were looking at a range of like planetary rotation speeds, etc. And so we're not looking at specifically the troposphere or the stratosphere. Yeah.
It's an Earth-like model, if I recall, but in which they varied the rotation speed of the planet. At a higher rotation speed than Earth, you get multiple jets. And what Kemper and Caspi found was that these jets would drift systematically forwards. But the mechanism that they invoked, if I can just join in the discussion, I think they were emphasising the fact that this is not a beta plane, that it's the spherical curvature and the fact that effective beta is itself a function of latitude that would break your...
Yes, so in these simulations, there is a natural symmetry breaking mechanism due to the spherical geometry. And so that's why in these cases, you only see migration in one direction. You don't see the spontaneous changes of direction. What's different in the models that I was showing today is that there's no obvious symmetry breaking mechanism. Okay, so something else is happening internally within the system to break that symmetry.
Yes, one more. Yeah.
So the -5 thirds range in your spectrum is coming from inverse cascade.
Yes.
And I wonder the same tendency continues even for larger scale, or something different happens in terms of the energy cascade.
Well, if I go back to my data, yeah, so this is from one of my simulations. This is the K to the -5/3 spectrum that you were referring to. However, this is a rotating system, okay? And so what you see at larger scales is instead a zonostrophic cascade, which has a K to the -5 spectrum given here.
So there's no inverse cascade or enhanced inverse cascade in that regime, or you don't know?
I'm not entirely sure I'm understanding your
sorry
question.
about that. Usually inverse cascade regime, entropy is cascading, forward cascade.
Yes. Yeah.
So the same tendency for the, larger scale or not? That was my, first question.
The K to the -5 part, though, doesn't that only apply to the zonal mean or the zonally symmetric component?
No, it applies to the largest scales, basically.
Okay, that's different, I think, to what some other studies have found.
Okay. Yeah.
Those scales are feeling the beta effect, though. That's
Yes.
That's what I think the answer is.
Yeah.
Okay, one more.
When you were showing the different lambdas, lambda equals 0, 1, etc., if you can go back to that plot, please. to some extent, were you lucky just cutting lambda equals 1, or do you have a general argument? Because whenever you go, for instance, if you look at lambda equals 2, should you cut there? You see a very different behavior, for instance, of your jet. So do you have a general prognostic argument as to where to cut based on what you have observed?
So in my simulations, I mean, this is one particular example, but I obviously I have a lot of different examples as well. And I see the same thing in every single case. That always, when you go to lambda equals to 1, do you start to see the same types of nonlinear behavior appearing, okay? And the reason for that is that we're allowing the formation of zonal wave numbers equal to 1 to come into play in the system. And those are what we associate with the zonons. Okay, so once you allow zonons to form, then you start to be able to reproduce the dynamics from the fully nonlinear model.
Okay, sounds like that's a topic for discussion over a pint somewhere. Perhaps we should wind up at this point and thank Laura again for